Hello, my steel design friends. In this video, we're going to work some compactness problems and try to do some beam design for simple lambda type problems that we've talked about in previous videos. So without further ado, let's get started. So the first problem that we're going to look at is a simply supported beam subjected to a uniform load over a span of 20 feet. Okay, it's pinned at the left, roller at the right. The dead load is going to be taken as 0.2 kips per foot. This does not include self-weight, and then the live load is going to be 0.8 kips per foot. Okay, we're going to assume that the compression flange is fully constrained. Okay, this is our scenario where we say LB is equal to 0, that it's braced along the entire length. Now, the question becomes, which flange is the compression flange? Well, for a simply supported beam, we pretty much know that compression is in the top, tension is in the bottom. But if this were a cantilever beam or compression was in the bottom flange, you'd have to make sure that the bottom of the beam were restrained in order to be able to meet this criteria. But for us, since we're studying the lambda effects, this is the assumption. We make this assumption every single time. So we're going to work it two different ways. We want to find the lightest section of A36, and then I want to find another one of A572 grade 50. Or if you want to say this is A992, it will be the same material properties as that. Again, this is a bit of an older example. Okay, so here's what we're going to do. So obviously the first step that we need to look at is we are going to factor the loads. So our factored distributed load W is 1.2 dead plus 1.6 live. If I plug all those numbers in, I get 1.52 KLF. Okay, the maximum moment on a simply supported beam we know is WL squared over 8. So the factored moment that we're going to design for is WU L squared over 8. So I'm going to do 1.52 KLF. I'm going to multiply by 20 feet squared divided by 8, and I'm going to get a capacity of 76 kip feet. Okay, now one of the things that you got to be careful on is since all of the section properties in US units are measured in inches, that kip feet will be a problem. So we're going to have to convert that to kip inches at some point. I'll do it a little bit later on, but just keep your eye on that, and you'll see that 12 show up here in a second. So now we're going to do our first scenario. For A36, what are we going to look at? Okay, so we're going to assume for now, in order to just get kind of a preliminary guess on the size, that our section is compact, meaning that we're in the region 1 of our graphic, if you remember that from the last time. And I'll pull that up here just a second. This guy. Remember we were setting our graphs for compactness criteria, look something like this, where it's MP in region 1, it is linear in region 2, and it is thou shalt not go there in region 3. Okay, so if we look at this, the criteria for this is that lambda has to be less than lambda p. And that's for both the web and the flanges both. You have to check both. Okay, and so that's where we're looking. And so we're going to assume right now that we're in region 1, and we're going to try to size our beam to hopefully stay within that region. Okay. Okay, all right, so here's how we're going to do it. So if it's region 1, then the nominal moment, mu, is going to be equal to the design capacity, phi mn, okay, is going to be equal to phi mp. This is the region 1 criteria. Okay, and if that's the case, then MP we know is ZXFY for an I-beam orientation. Now again, we're assuming continuously laterally braced compression flange, meaning that there is a concrete slab or shear studs that will keep that beam from wanting to roll out of the plane. Okay, that it's only going to deflect in the vertical direction. It's not going to try to roll over and experience any of the other more complex, ugly scenarios that can happen. So all I'm going to do then is I'm going to take this equation and rearrange it and come up with what is my ZX required. Okay, and so to do that, I'm going to solve this equation for ZX. It's going to be mu over phi over Fy. And so for a 36 KSI beam, we're going to be looking for a ZX that is 76 kip feet times, here's that 12 inches per foot I warned you about, so make sure that's in there. And that's just to get the units to work out, divided by 0.9, divided by 36 KSI, and my ZX required is now 28.1 inches cubed. All right, so if we go through our tables on there, and I will go pull this up for you. Let me pause the video for just a second as I get the manual open. All right, so I've got my steel manual here, and I'm going to show you a couple of different ways that you can do this. Again, since we didn't specify a depth of the beam that we were looking for, I'm going to go pull a bunch of them. Now, there are two ways that you can do this. You can go back up into table 1-1, and I can start reading off ZX values and trying to find those, and there's a bunch of them. Okay, and it's not hard. You just go look at the W8s, find the first one that works. Try, W10, first one that works, so on. I'm going to show you another way, okay, but you got to be careful when you do this. So we're going to take a look at then this table 3-2 that is located, it starts on page 3 dash, what page is that? Let me get the page flipped over here. On 3-20. Okay, now you probably see the one problem, the one thing I'm going to warn you about is that these tables are set up for 50 KSI, okay? But you can use them because what they've done is they've ranked all of those sections from from that table up in section 1, they've ranked them in descending order of ZX, okay? And so I actually have the ZX value present here. And so this is a very useful table for quickly finding the smallest one larger than a specific number without having to scan through page upon page. What you can't use this table for is to go in and pull moment capacities or LPs or LRs or any of the other stuff on the table. You can only use this first column. Okay, so if I go through and I look at this, let's go back, and so we want to find what value were we looking for. We were looking for 28.1 inches cubed, so we're going to be way at the back of the table on this. Okay, so that's what I'm going to set myself up for here. Let me zoom out just a little bit. Okay, and so we can kind of start looking. So we're looking for 28.1, and this is what's nice about this. Okay, and the way these tables are set up is a couple of different ways. Okay, but we're looking, the ZX column is this column right here. If I slide this down a little bit, you can see everything. All right, so we're looking for 28.1 as our first number. So the first one that we come to is 29.3. And you'll notice some of these values are bold and some of them aren't, but they're kind of grouped together. And what happens is some of the section properties, when you have them, that if I say I chose, my number was only 27.1, I might choose this guy. But if you look, the guy that's directly above him in bold is actually lighter than that one. So whenever you're in these groupings, if you're down in one of these that's not the black one on top, you can automatically jump to the lighter one that is the darker one up above. Okay, so we're looking for a W12, 29.3. That's greater than my 28.1. This would be a candidate for us, okay? We could also jump up to a W8 by 31 who has a value of 30.4 and a W10 by 26, 31.3, and so on and so forth. So really quickly, without scanning all those pages, I can pull a ZX value off of this table just by looking at those values. And that's what I've done on our table here. And so all of those values that we just saw are the values that we pointed to. Okay, so my W8 by 31 is 30.4, my W10 by 26 is 31.3, my W12 by 22 is 29.3, and W14 by 22 is 33.2. Those are my ZX values. And so if we want to choose, okay, then we can go through and we can figure out, well, which one do we want to take? And it's obviously the one that's the lightest weight. Okay, so we're going to take either the 12 by 22 or the 14 by 22. This is actually the lightest standard W14. Okay, it's the same weight, either will work. Okay, so what we can do is, well, how do you break that tie? And so we'll get into some calculations that we'll do eventually called serviceability calculations where we're measuring deflections. Okay, and deflections are functions of the moment of inertia, and the deeper the section, the higher the moment of inertia. Often, if I can get away with it, I'll take the larger one because it will help control my deflections a little bit better. Okay, but there's lots of ways to break the ties. But for us, we don't really care. I think in this one, I actually went ahead and chose the W12. Okay, so W12 by 22 by 20 foot long. Now, there is one thing I want to point out to you that we'll point out here is that if you look real close on that W8 by 31, there was an F superscript that shows up on here. Okay, and you can see it if we zoom in. Where is my 8 by 31? That's the bottom one here. See that little bitty F that's kind of superscripted up there? If you can't see it in the book, pull out yours and take a look and you'll see it. And what the F is, if you look down at the bottom, and that F shows up even up in the tables up in the front of the book, but the F down here is this first note. And what it says is that shape exceeds compact limit for flexure when Fy is equal to 50 KSI. Okay, so tabulated values have been adjusted accordingly. So what happens is that by that, what that means is that in our diagram of our shape, that means that your lambda for the flange F is not in the compact shape section. It means that what's happened is whenever that F superscript shows up, you have actually rounded over this corner and you're now sitting down here somewhere where lambda is in this range. And so these capacity calculations that they're doing, they've modified and they've used this formula to correct for it. Okay, so it's not an MP formula. Now, again, we're dealing with a 36 KSI beam. In this example, it doesn't matter, but that's how we start to choose it. So our beam that we choose based off of the compactness criteria is is a W12 by 22, and that's the way that we would start to kind of choose that. Okay, now, we did make some assumptions. We didn't check compactness. We chose based off of Z, and we assumed up here that it was a compact section, meaning that we assumed that the lambda for both the flange and the web were less than lambda P. Now we need to verify it. And so this is how you do it. All right, so to check our compactness assumption for a W12 by 22, okay, for the flanges, lambda is equal to BF over 2TF. And if you look this value up in the table, as I showed you guys last time, this BF over 2TF value is 4.74. This comes from the section properties table. And for flanges, we're going to check this guy, this 0.38 EFY. So our assumption that we're checking, we're wanting to know, is lambda less than lambda P? Is that a true statement? That's the criteria. And this is for web, okay, and flanges both. Okay, if one of them fails this check, the whole process is flawed. We haven't met our assumption. So we're going to take the 0.38 square root of E over Fy. That's going to be 65 over the square root of Fy for our number if we do the math. Okay, and so if I plug in all of this, here's my 29,000 for E, my 36 KSI for that. And so this whole number becomes 10.78. So 4.74 is indeed less than or equal to 10.78. So we're okay for the flanges. And generally, if you're okay for the flanges, a lot of times you're okay for the webs on the standard shapes. Okay, now for the web, we're going to check lambda is equal to H over TW. Okay, and so for lambda P, for this, that's the 3.76 formula, square root of E over Fy. If I do the math and simplify it, 640 over the square root of Fy for 36K, for E of 29,000. Okay, so my H over TW for this beam is giving us 36.2. That again, that's from the section properties. And if I do this calculation with 36 KSI for Fy, his limit is 106.7. So we have plenty of room to spare on the web. Okay, not as much on the flanges, but on the web we're plenty okay. So that means he's okay. And because both of these are okay, I can now make this statement that the beam is indeed compact as we had assumed. Okay, now some things to note, and I kind of hinted at one of them. Okay, standard W and C shapes are all compact for the web when Fy is 50 KSI. Every single one of them in the book, without exception, that is a W and a C shape, will meet that compactness criteria. So you really don't even need to do this check. Now, if you're one of my students taking a quiz or a test, I will expect you to do it just because you need to know that you don't need to do it. Okay. The other one is that most flanges are compact as well, except for the ones that have that little F that I just showed you. Okay. So if you choose a beam that has an F on it, you know that you're non-compact. Okay. Or partially compact, I guess is the right word for it. And you're in region 2. So you got to be kind of wary of that F that's sneaking around on you. Okay. All right. So that's how we do these types of example problems. All right. So let's try another one. Just kind of give it another shot and kind of work through it kind of in a similar fashion. All right. So now I've got a beam, another simply supported beam, kind of the same type of problem. And again, if you want to try to stop the video and try to work through this on your own without looking at the solution, that's fine. Okay, so what we're going to do is we're going to basically come through simply supported beam. It's now 12 foot in length. WU is 1.52 kip per foot. And then the MU, factor moment, is 76 kip feet. Okay, we want to choose the lightest W12 shape of A572 grade 65 on this. Okay, so just like we did before, we're going to solve for ZX required. That's going to be MU over phi Fy. Okay, again, watch your units. 76 times 12 inches per foot over 0.9 over 65 KSI this time, and now our Z is 15.6. Okay, so then we can go back to the tables that we just showed you. I need 15.6. Again, we're in the really small regions of this thing, and so 15.6 gets me into this grouping. Okay, and so if we look 15.6, I could do a 10 by 15, I could do an 8 by 18, or I could take the 12 by 14 as the lightest alternative. Okay, now you'll notice it too has a superscript, but it's not an F, so I'm okay. This superscript is actually a V, which tells you that you have an issue with shear in the web, but we'll cover shear here in a couple of weeks when we get a little further into the beam design. Shear is a pretty easy thing to fix as far as like stiffeners and doing some things to stiffen the web. We can kind of resolve that issue, but it's kind of, and generally shear capacitors are very high for most steel beams, and it's not an issue for normal structures. So for us, we're going to take a 12 by 14. That's the size that we're going to take. Okay, again, we're doing a 50 KSI table. That was up here. Okay, but our strength on our problem is 65, so we do need to check, but we're just using a table to get the ZX values. All right, so here's what we're going to look at. If I go through and I look, okay, we're going to check the web. So again, what we assumed up here, we assumed lambda is less than lambda p, which means then that mn is equal to MP. That's what we did up there. That was the assumption that we did. So make sure if you do this as your route on solving a problem, you have to confirm it. Okay, so if we do our web for this W12 by 14, the ZX was 17.4 inches squared. We're going to check the web, and that's the H over TW. So 54.3 is its parameter. We're going to calculate 3.76 square root of E over Fy. Tells me that value is 79.4. This is less than that. The web is okay. Okay. And again, we know that for 50 KSI, all webs are compact, but again, we're doing a 65, so that's not the case here. Okay, the lambda for the flange, we do the same thing, BF over 2TF. Okay, and so I actually calculated it instead of looking it up in the table. This value is 8.8. Okay, I actually plugged in BF and TF and 2, but instead of looking it up, but it's 8.8, and then we're going to compare that to 0.38 square root of E over Fy. Okay, and what happens on this is this 12 by 14 is, if we look, should be 8.1. So this is actually no good for the flange. Why did that not have an F? That's interesting. Okay. Oh, well, F is for 50 KSI. So it's also not good for 65 KSI. That's why it didn't have an F, and why it failed on this. So this one actually, this 12 by 14 is actually compact for 50 KSI, but it's not for 65. Okay, so it's no good. It means that this is in region 2. This guy was a region 1. This guy was a region 2. Okay, and you take the worst of them. So this is a region 2, and the flange is what's going to control. So we need to go modify our formula. Okay, and so for this, what we've concluded is that lambda p for the flange on this, lambda p is less than lambda, so this is region 2. Okay, we now need to go calculate what lambda r is for the flange. Okay, because we're trying to find out, are we in region 2 or did we really mess up and end up down in region 3? Okay, all right, so the way we do that, we go pull the lambda r formula. This is for the flange. Okay, the lambda r is 1.0 times the square root of E over Fy. This gives me a number of 21.1. Okay, our lambda was 8.8. So this is 21.1, and this is 8.1, and this is 8.8. That's the region that we're in. So this is region 2. Okay, that it's non-compact or partially compact, but it's not slender. So now I can go in and I can do my moment equation, which is this interpolation function that we had, and we basically just plug in everything that we have. Okay, so here are the parameters. It's MP minus the sum of MP minus MR times lambda minus lambda P over lambda R minus lambda P. And we're bound by the upper limit of MP. Okay, so MP for this beam is ZXFY. ZX is 17.4 inches cubed. Okay, FY is 65 KSI. And so we're going to divide that by 12, and my capacity is 94.2 foot kips is the plastic moment for this guy. MR is taken as SX times FY minus FR. And Fy is the yield stress. Fr is kind of a residual stress that lives in it and is normally taken as 10 KSI on this. So we're going to take our Sx parameter, which is 14.9 for our beam. Again, we're looking at a W12 by 14 is what we're looking at. So I'm pulling all these section properties for this beam. Okay, and so when I do this calculation, I can do 14.9 times 65 minus 10 divided by 12. Gets me an MR moment of 68.3 foot kips. Okay, and so we needed, how much did we need on this one? We needed 76. Right, so if I need 76, you can see that we're in between these two. We're going to be okay, but let's go ahead and figure out what the actual capacity of this beam is. Okay, is that Mn then is 94.2 minus 68.3 times those lambda functions. So here's my lambda, 8.8, lambda p, subtracting, and then lambda r minus lambda p. Okay, and so this moment is 92.5 for the beam that we chose. And so you can see it's a little bit less than 94.2, but we're still, again, going back to our picture, this picture, we're way up here. We just barely went over the edge before we had a problem. So we're still way up here. We have a really high capacity. I wouldn't worry too much about, economy or loss of economy by choosing a bad size. This one's actually pretty good. Okay, so that's my 92.5. That's my MN value. So now I need to figure out what phi MN is. Okay, so I'm going to multiply that by 0.9. So 0.9 times 92.5, that gets me 83.3. That's greater than my MU, therefore we are okay. So we can choose a W12 by 14 with an FY of 65 KSI. And this was a region 2 problem. Okay, so again, we chose the worst one. If they're both in region 2, then you got to run the MN for both. Okay, but again, for standard shapes, the webs for 50 KSI, it's not very often an issue, and it's usually the flange is the one that gets you in trouble. Okay, so that's kind of a secondary thing to think about as you're starting to kind of work your calculations. So I hope that's made sense to you. A couple of examples to kind of get your feet wet, whet your appetite, whatever the case may be. If you've got any questions, leave some comments down below. I'll be happy to answer them. Otherwise, please like the video and subscribe to the channel, and we will see you all in the future. Have a good evening. Bye.